Good afternoon. I just, with this presentation, wanted to give you a flavor of the manufacturing automation projects in small to medium-sized enterprises in a Norwegian context. One project in which I will detail is the metal casting gripping project, which is quite close to the presentations you had yesterday from Charlie and Walter. So I am an associate professor in Høgskolen i Gjøvik, which is officially a part of NTNU from January next year. And NTNU is where I did my PhD also, so in a way I did a full circle, and I'm a part of the French Production Academy as well. So the Norwegian Centers of Expertise, this list, most of the money that exists in Norway is from oil and gas, and previously it was agriculture. So there are many Norwegian Centers of Expertise, and I am related to the NCE Raufoss, which is 2 hours north of Oslo by train. And they are the ones that are doing most of the projects in manufacturing automation, a lot of projects with Chalmers as well. From a Norwegian standpoint, when you look at the price of a robot versus the salary of a Norwegian, average salary of a Norwegian worker, if you looked at around 1976, it was about 8 times as expensive to get a robot to work the same amount of work as a person to do that. And about it cut through in 2011, it's almost the same. So the projects I'll show you today are, if you can consider fundamental research and industrial research, it's more an implementation project. It's not basic science or new technology. It's more implementation where new technology becomes available. It's a BIP project from, I cannot translate it into English from Norwegian directly, but it's a BIP project, which means that you are making the existing technology available to the small, medium enterprises. The participating companies for the AutoCast consortium, the companies, they were mostly metal casting companies. So Jotun is an iron casting company, Farsund is an aluminum casting, and all these companies are towards the southern coast of Norway, and Norsk Industry is industrial consortium of the companies, which all these companies are a part of. The process from a manufacturing standpoint, since Jotun was the lead sponsor of the project, and the project was about 9 million over a period of 3 to 3.5 years. It was industrial PhD, that's industrial PhD program. If you look at the process that Jotun had in Fredrikstad, which is another city near Oslo, they were recycling old ships. I mean, they melt the old ships and they cast the iron into home ovens, and they were individually blasting the parts. There was manual sorting of the parts, and then there's 2 processes, the finishing operation and the enamel coating of the ovens before the assembly and shipping to the customer. This is how a part would look like. These were the people, they were full-time employees at Jotun. This was a hardware engineer, a software engineer, and the director of quality, which were involved in this project. So most of the basics of grippers and gripping handling were done yesterday. But I took this picture from one of the papers, the scientific publication, where how do you select a robot gripper? You look at the component you're going to handle, the task the robot has to do, the environment, the robot, the kind of robot, the gripper, what it has to do in general. And of course, we had safety and energy, which was from the workshop today. So different gripping solutions that were considered by the main company were, for example, pinching grippers, which exactly did not suit their needs. So you have 2-finger, 3-finger grippers, which are quite standard. But these grippers are not so good with handling flat parts. Of course, you have vacuum grippers, which can handle flat parts. Also sand cores, which are used in casting. But they have a limitation of, they're very, very fast, and they're quite bulky. So this is roughly 20 kilograms. It was a huge gripper on a rack in the company. Cornell came to us with different solutions. This was a jamming gripper that was shown by Charlie yesterday, but this was an individual experiment that I did it myself with Cornell to check if they were really, the grippers were as good as they were claiming it to be. And sometimes it works, sometimes it doesn't work. For the videos you see in the marketing videos that they show, it looks like a perfect gripper, but it doesn't have a very good position accuracy. But if you look very closely below here, there was a marker point that they were place the part exactly. If the gripper knows exactly where to pick, it works. And if it's a 3D profile, it works very good. And Stanford came up with their Stanford seabed rig hand. They said it was an original invention, but then if you look in the literature, it was already done in '98 by another person. And yeah, it also had a limitation of handling flat parts. It could not do a very good job. So I took this picture at the Stanford laboratory here in the robotics lab. So Yotel did not quite, was not very satisfied what they were seeing with the solutions that were existing. Of course, we also looked at the German DLR hand, which was shown yesterday. Also, the Utah MIT hand, which are it's quite expensive. Of course, it's $500,000 each hand. But it's not practical right now, but could be practical in the future. And MIT has a compliant gripper section. Since I went to U of M, I went back to them to see what they have to offer for the Norwegian companies. So they came up with this topological synthesis. You pull the gripper from the side, and you have this force that comes and picks the part. It's very conceptual, not so practical. So Yotel decided to develop in-house using their engineers. For example, they started small. Since most of the parts are recycled from ships, they are cast iron. So you could use a DC magnet to hold these parts. So for small flat parts, you could easily use a DC magnet. And for handling bigger parts with complex profiles, you could easily have a flexible, reconfigurable gripper doing the similar job. But the limitation is, of course, you can make these arms extend to handle different parts, but they are still flat grippers on the bottom. So for special parts that look like this with a curvature, we had to experiment to find the right kind of optimum geometry to handle various complicated profiles, and we had to end up designing our own electromagnet. The third version of the gripper was a little bit more flexible when we did some experiments and trials. There was a third-party vendor called Scorpion Vision, which is also based out of Oslo, which was used to provide the service for the vision system software. Did some tests from picking the parts from the conveyor belt, bin picking problems, placing it on a fixture, which is nothing really new. This gripper is also quite heavy. It's roughly 20 kilograms. And the problem with this gripper is it tends to crash when you are throwing parts in a real environment. In a bin, it would crash on these two edges when it was being stacked from a bin picking problem. Also, the vision system, it was very difficult. I could not find a good solution for any vision system in the market, which can be used for, and structured light is no good, for cast parts. So we tried different markers, so circular markers, straight lines. The problem was that when you throw the parts in the bin, and if the part is tilted more than 30 degrees, the straight lines just disappear here. You cannot tell nothing at all. But there's always a certain part of the circle which is visible. And cast parts generally have some special problems because when you're mixing and melting metals, different metals, they show certain profiles, and mixture of metals can be detected on the surface of the parts. So then we had the fourth version which was developed, which was more reconfigurable, which could adjust to different profiles of the parts. And of course, if you use the grippers, which are the magnets, which are already there in the market, you could get 1/3 the size and 10 times the holding force. But because the parts were so special, we had to design our own gripper. And the only example which exists in literature is from electromagnet grippers in foundries in Japan. And I haven't seen it in operation, but this is a plant near Tokyo. So we did our own lab experiments. Studied the core composition of the electromagnet, the iron plates, the part geometry, the surface roughness, the BH curves, and did some simulation on part stacking scenarios when the problem with electromagnets is this is a cross-section. That's the core of the magnet, that's the outer cover, that's the part, and that's another part. If you have two parts, one after another, two plates stacked one on another, the holding force of an electromagnet changes. It's very sensitive. If it gets scratched, the force changes again. So, but this was a final installation in the finishing cell where the robot was installed. We got this lift from Sweden. I don't remember the name of the vendor yet, but I can give it to you later. The parts are stacked in the finishing cell. Both the fixtures and the parts are taken, and this is the gripper that's put in, it was the 4th version of the gripper that was developed. We used RFID at the base of the CNC machine, and we tried to make this operation as unmanned as possible. And of course, RFID readers are attached to the base of the CNC machine, and the tags were at the base of the fixtures, and different operations were carried out. Integration of this cell with the plant-wide traceability system was done with another third-party vendor. And an HMI was developed where you could see that which part is lying on the pallet in the storage rack, which part is detected by the vision system, what part is on the robot, if it's completed or not, if there were any problems doing that. And of course, there are many different challenges which are still existing right now because there are so many complicated profiles which need to be handled. You need a closer coupling between different manufacturing cells. You could use RFID tags to incorporate and integrate different part handling systems within the company. And this is another technology which was developed by Penn State, which they offered to integrate. This was used for magnesium castings. It's a glue. It's for whenever you machine a part or a casting, you have clamps that hold the part. So this is a clampless process where you put a glue when you put the part on top of the fixture for machining. So this is a magnesium casting, and then you turn it around and do a curing process with showing a lamp light at the base of the glue. So the glue hardens, and then you have the machining operation without any clamps holding the part. So I published a book which was, I could not find anything in the literature which talked about metal casting automation. So I wrote a book for the American Foundry Society. And there are other manufacturing automation research initiatives currently going on. One is with adaptive control with the sewing process of furniture manufacturing and how to automate it in the furniture industry. Also, kind of linking automation with lean in general. And of course, everything has their own challenges with fast design changes and craftsmanship. And when two robots are trying to work together to hold flexible material, it's quite a big design challenge. There is a learning factory incorporated working with the industry, academia, and the government. It's very close to the Volvo learning factory that they have in Sweden. And the concept is you work with industry on similar problems. Students come and work on, this is a lean Kanban system flow that they were training the industry and the students together on. So it's a common space that the people come together to exchange ideas. So I guess that's all I have to say.
How many different parts are you supposed to handle in the station that you?
Well, the company identified about the biggest parts that they had was 60%. So they still had 40% of small random parts, which they are manually handling because there is no one flexible universal solution available. So yeah, it was kind of an open issue. And also, they just wanted to look at handling heavy parts with sharp edges, which were really painful for the workers. So they just wanted to get that out of the way. The smaller parts are much more, at least not that painful at the moment.
Yeah, thank you for a nice presentation. My question is, in addition to the grippers, did you find any other issues in the robots for this type of applications?
Yeah, well, the robots have to work with extreme conditions, temperature, humidity. Couldn't find good solutions. There's a 6400 series that ABB has for foundry applications. There's no small-sized robots. There's no good robots for handling hot parts. Certain conditions where the dust is too much, where they have cores. So there are certain areas where I would say there's more hazardous environments within the foundry, which don't, this is more assembly operations. The parts are, okay, they have sharp edges, but they're still at room temperature. So the heavy parts that the humans don't want to handle or they want to take away from manual handling, they could easily incorporate automation in it. But yeah, those are some of the challenges. And then vision systems are not very well developed for foundry operations from a scientific perspective, yeah. So there are many open research issues in foundries. And I couldn't find much publications. I wrote a lot, almost 30 publications. That was the reason I could get my academic position. But I think not many foundries. It was easier in Norway and Sweden to do it. The foundries were very open. They were getting money from the government to pursue such a project. They could buy robots. They could buy the finishing cell from Sweden. They could buy certain parts. So it was also the whole thing that came together to bring this project together in action. And 9 foundries came together to work on it. But finishing is another issue, an open research issue, because you cannot get accuracy more than 0.3 millimeters in finishing. When you're using grinding operations on using robots to grind cast parts. So when you just want to look at finishing operations, that's a whole also another open issue, because they have open loop control systems in that. There is no closed loop feedback force control in that.
I was just wondering if you spoke anything to Volvo Aero or GKN.
I visited Volvo Aero in Kongsberg.
Yeah.
No, not yet. Not the finishing operation. They were working on MRP systems.
Okay.
But I would love to see what's going on. I mean, I visited Rolls-Royce.
Because they should have similar.
Yes,
issues.
similar painful, issues. I would say you're right.